Rosen, Discrete Mathematics and Its Applications, Section 1.8, on Proof Methods and Strategy. In this discussion, we'll talk about proof by cases and without loss of generality, and here are the other topics covered in this section. Proof by cases tackles the form of proof where we have a disjunction of several propositions, and if any one of them is true, then Q is true. So we'll use the tautology that the disjunction of propositions implying Q is true is the same as each one of those propositions implying Q is true are disjoined. And each one of these will be a case. Here's an example. We're going to define the operation given by this at sign right here as if a at sign b is just the function, is just the max function for a and b. So if a at sign b is equal to a, if a is greater than b, greater than or equal to b, otherwise a at sign b is equal to b. So it's the result of the max function. And we want to show that for all real numbers a, b, and c, that the max of a and b taken, the result of the max of a and b taken, then the result of that with c is the same as the result of max of b and c taken, and the maximum of that result is a are equal. In other words, that this at sign operator is associative. Okay. So we're going to let a, b, and c be arbitrary real numbers. There's going to be 6 cases that we need to prove this for. If a is greater than or equal to b, and b is greater than or equal to c, or every possible arrangement of a, b, and c with respect to each other in terms of greater than or equal to relation. All right, go to the next slide. We'll prove it for case 1. So for case 1, if a is greater than or equal to b and b is greater than or equal to c, well, the result of the max function of a and b in case 1 is a, and the result of the max function with a and c is a, and the result of the max function with b and c is going to be b. So the max of a function with b is going to be a, and we know that the a function with c is going to give us a. The max of the b function with c is going to give us b, but we know that the max of the a and b function gives us a. So they are equal in case 1. We haven't completed the proof though. In order to do that, we would need to do the similar analysis for all 6 cases. And I encourage you to do them. It's pretty straightforward, as you can see. And it's good to go through that exercise. And once you do that, we would get the left-facing black triangle. All right, another aspect of doing proofs is called without loss of generality, when you can make an assumption about several variables, but it doesn't change the case if you switch the variables. Here we have a problem. We have x and y are integers, and we want to prove that if both x and y are even, then, if both x times y and x plus y are even, then both x and y are even. And I'll call this P, and I'll call this Q. We're going to do proof by contraposition. So we're going to do a negation of Q implies the negation of P. And we're going to suppose that x and y are not both even. So that is going to be the negation of q. And we need to show the negation of p. So since p is x times y and x plus y are even, we only need to show that one of those two operations results in an odd number. Now, back to without loss of generality, since x and y are commutative in these operations, we're going to say without loss of generality, we're going to assume that x is odd. Okay? We could assume that y is odd, but it's going to be exactly the same analysis. We're going to say without loss of generality, assume that x is odd. And then we'll apply the definition for x to get 2m plus 1 for an integer m. Now we have two cases. Now if x is odd, y could still be even, and in that case, y is equal to 2 times n. And then if we add them, we get x, which is 2m plus 1, plus y, which is 2 times n, gives us 2 times m, the quantity m plus n, plus 1, which meets the definition for an odd integer. And since the sum of x and y is odd, that proves the negation of p in that case. We have another case though. What if y is odd? If y is odd, then we can substitute 2n plus 1 for y, for an integer n, using the definition of odd. And this time we're going to check the product. So 2n plus 1 is x, 2n plus 1 is y. If I multiply those together, I show that I get 2 times an integer, 2 times m times n plus n. Then that result plus 1 is the product. That meets the definition of odd, and that also shows that you get the negation of p in case 2. We don't have to check the other aspect of p because only one of them needs to be odd in order for not p to be true. And we are done. We didn't need to check the case where y is odd and then x is both even and odd because x and y are essentially the same above, and that's without loss of generality.